Hi, my name is Perry Martins, and in this video, we're looking at the TensorFlow library in Python. Now, TensorFlow is a library in Python that is created by Google, and it's an open source machine learning framework to carry out high performance numeric computing, particularly when you want to work in the area of artificial intelligence, neural network, deep learning, deep neural network. You need TensorFlow because it makes the data preparation in such computing very easy. So we'll be looking at the TensorFlow here. We'll be looking at the data types you have in TensorFlow, the constant, the placeholder, and the variable data type. I'll look at how you create the computational graph and the tensors in TensorFlow, because with TensorFlow it's a blend of two words, the tensor and the flow. The tensor is the data structure and the flow is the computational graph that you have created. So we'll be looking at how you create the tensor, either a constant tensor, variable tensor, a placeholder tensor, and how you create the computational graph, which is the flow aspect of the TensorFlow. Alright, so without wasting time, let's just switch to our Python in VS Code. Okay, here is my Python, and we are looking at introduction to TensorFlow. Now, TensorFlow itself is a blend of two words, the tensor and the flow. Now, the tensor is the data structure, particularly when you are dealing with data structure that are very complex, which are the case in neural networks. So, tensor helps you to be able to structure your data appropriately. So, tensor is the data structure, while the flow is the computational graph. So, the blend of the two words now makes the TensorFlow. And like I already said, it was created by Google, and it's very popular for complex numeric computing. Now, the TensorFlow itself does not come with the Anaconda package. So what you need to do is to go to your Anaconda prompt and do the pip install TensorFlow into your system so that I can have TensorFlow. Now, there are so many versions of TensorFlow. You have the version 1, version 2, and all of sorts in that manner. So based on the version you have, there might be some compatibility issues with the TensorFlow library. In this case, I have the version 2. So this first line here is what I've used to import the TensorFlow itself. So import TensorFlow as TF. However, because I'm using the version 2, there are some compatibility issues between version 2 and version 1. So that is why I'm using this line, import tensorflow.compat.v1 as TF. So this one makes my version 2 compatible with some workings of version 1. That's what that line is doing. And also here, tf.disable _v2 behavior. So here I'm using this line to turn off or to disable some of the behaviors of the version 2 that I have on my system. And this line here, I'm only using this line to import warnings, so that from this line, warnings.filter warnings in parentheses ignore, so that this one can help me to ignore all the warnings that might be as a result of these compatibility issues. So, but if you have the version 1, you don't need to do all of this. All you need to do is just to import TensorFlow as TF. So I'll just go on and do that. Now, TensorFlow is a very large library, so it takes a while to load. Now, this only took 0.1 seconds because I've already loaded this initially. It might take about 20 seconds to load if you are loading it up for the first time. Okay, so the next thing you want to know is what are the data types in TensorFlow. Basically, there are 3 data types: the constant, the variable, and the placeholder. So for constant data type, these are data types that the variable or the value that is stored in such data do not change throughout the course of your program. So if you want to specify a data type in TensorFlow as a constant, you're saying that the value that you have stored in such a variable will not change. However, for the variable data type, these are variables that will change. These are data that will change in the course of your program. That's why they are called variable data type. So if you know that a certain identifier would change its value in the course of your program, then you specify such a data type, such an identifier as a variable data type. And for the placeholder, in the case of the placeholder, you already know the value of the placeholder. However, at the time you are specifying an identifier as a placeholder, you will not put the value of that identifier there at that time. You only create that tensor, that okay, this tensor is a placeholder, which implies you are going to put the value of that tensor later. Most times you will find such value for placeholders at the time you're actually running your tensor. So you find the value in a dictionary in the TensorFlow session. When you're actually running your tensor, that's when you supply the values of placeholders. But when you create placeholders in Tensor, you don't put the values there at the instance, but you put the values when you're running the tensor as a dictionary. So that is for the placeholders. Now to check the version of your tensor, you can just use this line to check the version of your tensor. Print, this is the acronym which I use to import the tensor, tf dot double underscore version double underscore. This will give you the version of your tensor or any library that you have on your system that you want to know the version. Just put the acronym by which you import the library and use the same line. It's going to tell you the version of that library. So in this case, I have the TensorFlow version of 2.80. So it's the version 2 TensorFlow that I have on this system. Alright, so the first thing I want to do here is to show how you can create a tensor. Now we'll create a tensor by using the keyword or the acronym by which you import tensor with. So in this case, I'm creating an identifier LO underscore constant, and I'm saying this identifier LO underscore constant is storing the value of this. Now I'm saying that this LO underscore constant by this tf dot constant, I'm saying this identifier is a tensor itself, is a constant tensor data type. So tf dot constant. If it was a variable, I would have said tf dot variable. If it was a placeholder, I would have said tf dot placeholder. We'll still show all of that, but now by just showing the constant data type for tensor. So LO underscore constant is just an identifier. You can use anything here. So equals tf dot constant. This is saying that okay, this is a tensor and it's a constant data type of tensor. Now in parentheses, what is the value that it's holding? Like we said, for constant, you will supply the value at the time you're setting that tensor up. For variable, you supply the value as well. For placeholder, you do not supply the value at the time you're setting up that tensor, but you supply the value later as a dictionary when you are running your tensor session. So in this case, this is holding a string, and the string here is LO class. That is what the LO underscore constant data type of tensor is holding. So when I run this, what just happened was that this LO class has been stored in this identifier LO underscore constant as a tensor. Now if I just push in the same identifier here and I run the line, you see that it's not printing the string which is stored in the tensor. Let me create a line here and show you something. For instance, if I create an identifier A and I say A is having the value of 5, and I run this line and I come directly under it and I say A, because A is not a tensor in this case, it's just 5. You can see that the output was printed. But in case of tensor, when you create a tensor in this way and you run that tensor just by running the identifier, you will not get an output. However, you'll be getting something like this, telling you the data type is a tensor, tf.tensor, telling you it's a constant, telling you the shape. In this case, the shape is blank because it's just a vector. It doesn't have probably 1 dimension or 2 dimension. The rank is not given, and the data type there is a string. So you will actually get the output. So how do we actually get outputs in Tensor? Then we'll begin to look at that as we go along. Now, to actually get out the outputs that you have stored in any tensor, you need to run that tensor in a TensorFlow session. So there are two methods by which you would start up a tensor session. The first method is what I'm showing here. So the first method is this line with tf.session parentheses as ses. Now you can use anything here to do your acronym for the session. However, the standard practice is to use ses. So with tf.session parentheses as ses colon, in the body of that line is where you actually run your tensor. So I said my output equals ses.run. Now ses.run here is to actually run my tensor. So ses.run in parentheses lo underscore constant. So this line will actually run my tensor. So, and here I'm saying print whatever value is now stored in this output. However, I can use the print statement directly and put all of this ses.run lo constant directly into the print statement. It will still give me the run output of that session. So what I did here is to do what we call the building of a computational graph in TensorFlow. When you're doing a TensorFlow, the first thing you do is to build the computational graph. Then you now run your computational graph. So in building your computational graph, you create your tensors, you specify the mathematical operations that should happen, and when you are done with all of that, then you now run your session. We'll still show some other examples as we go along, but this is the first method by which you can run a TensorFlow session. You use the with tf.session parentheses as ses, then in the body of that line you will put the ses.run, the identifier you want to run, in parentheses. And in this case, I'm really using output here to store the value that is being run here into this identifier output, and I'm using this line to print what is stored in that. Also, I'm just using this one print function here to run the session and also put in my identifier that I want to run. So if I run this now, I will get what I stored in this lo underscore constant, which is lo class, which is what we actually stored here. So you build your computational graph, then you run your computational graph. This is the first method. The second method is this. You use the ses equals tf dot session. In place of using the with tf dot session parentheses as ses, in this case you use ses equals tf dot session. So you now do the running of your tensor. Output equals ses.run lo class, print the output, just what we did the other time, or I will just say print, and I'll put in all of this in my print parentheses. It will still give me the same output. However, with the ses equals tf.session, you need to close the session. Ses.close parentheses has to be there. With tf.session, you don't need to do the closing of the session. However, if you are using this second method of ses equals tf.session parentheses, you must close the session when you are done running the session. At this line, I'm done running my session, then I'm putting the ses.close here. So when I run this, you will see that we got lo class twice. The first one is for this, the second lo class is for this one. So that is the two methods, the ses equals tf.session method and the with tf.session parentheses as ses method of running the TensorFlow. Alright, so we'll go in proper into the data types in TensorFlow. Now the first is the constant. Now the constant data type in Tensor, by default, the class of that data is a float 32. However, you can specify as either float 8 or float 64, but float 32 is the default class of the constant data type TensorFlow. So like we said already, this I'm creating a tensor. X is the identifier equals tf.constant. So I'm saying this tensor X is a constant tensor data type, and the value that is stored in it is 4.0 because by default the constant data type for tensor is a float. So that means it must have a decimal place. So 4.0 is a float. So comma tf.float32. This is valid to create a constant tensor data type. This is also valid. Y equals tf.constant 5.0 because by default Python knows that for tensor the default class of data is float32. So if I put float tf.float32 here, or I don't put it, it's still valid, same as here. So like we said before, if I say print x, print y, nothing is going to happen because print x, print y does not run this tensor. I need to run the tensor in a tensor session. Okay, so what I'm doing here again is to create a computational graph. Let me just go to, so when we say we are creating a computational graph, we're saying that at the other end we saw x as a tensor, tf.constant. Also we saw y as another tensor which I created, tf.constant, and I'm building a computational graph after creating the data. This is the data, and I'm creating the computational graph now, and I'm saying x, y. I'm running the two into a sum block to give me an output of u. This here is my computational graph for this tensor I created, because that's what I'm doing here. You create your tensor, you create your data, your tensor data, then you create your computational graph. In this case, running this, printing u, we call it not print anything because I need to run this computational graph or these tensors in a tensor session. So when I run, you can see tensor constant 1.0 shape data type float32 for x, tensor constant 2.0 shape data type float32 for y, tensor hard equals 0, this equals 0, the shape float32, that is for u. But to actually get the output of x plus y, which is 4 plus 5, which is 9, I need to run u in a TensorFlow session. So you notice here that in Tensor, I don't need to run x, I don't need to run y, I only need to run u. Once I run u, Tensor will automatically go back to run other instances, to run every level of your computational graph. So you only need to run the last operation on your computational graph. Once you run the last operation on your computational graph, once your computational graph is well built, Tensor will go back to run every node that you have in your computational graph. So here I'm showing how to hard multiply two constants in a tensor session. So here is u equals tf.hard x comma y. We already created x and y here as constant tensors, and here I'm saying u equals tf.hard x comma y. So this will add the two tensors together in a TensorFlow session. And here again I'm saying v equals tf.multiply x comma y. This will equally multiply x and y. So I'm using the second method here. Ses equals tf.session. Then I'm saying my output equals ses.run u. So I'm running u. This is u that I'm running. So once I run u, u will run the sum, and that node equally will run the tensors x and y so that I can get an output. So here I'm printing what is stored in this output, and also I'm running another tensor here again because the session is still open. So W equals sets.run V. So I'm running V here. This V will run this multiply block, and the multiply block will run the tensors for X and Y. If I come here and I say that my K equals 5 multiply U, if that's my K, 5 multiply U is my K. If I create another session here and I say let me use R equals ses.run, and I'm putting my K in that, and I'm saying print my K, print K. So at the end I will need to close my session, because if I don't close my session will remain open. So once I run that, now we can see here that we have 9, which is the addition of 5 and 4 for U, and also we can see 5 times 4, which is 20 here. However, for the R, this will be K, this will be R, not K. So for the R, we can see that 5 times U is 5 times 9, which is 45. So that's what we have here. So you can see that's how you can have multiple tensor run sessions within a tensor session that you have opened. So I opened my tensor session here and I ran 3 sessions, 1, 2, and 3, and afterwards I closed the session here. So it's very important when you're using this method of ses equals tf.session. After you've run all your sessions, you must close your session with the ses.close. So the next other time we'll be looking at is the placeholder. Like we said, the placeholder, when you create the placeholder, you do not put the value of the placeholder at the other instance. However, you can put the value in when you are running your session as a dictionary or a feed dictionary. So here I'm creating 2 placeholders. So D is the identifier equals tf.placeholder. So tf.placeholder is telling Tensor that okay, this identifier D, it's a tensor which is a placeholder, and I'm telling Tensor that okay, it's a float, tf.float32. If it's an integer, I would have said tf.int for integer. So but in this case, tf.float, and also f equals tf.placeholder, and it's equally a float 32. So I'm creating my multiplier node now, multiplier underscore node. So here is where I'm actually building my computational graph. You know, the first thing, I'm creating the data type, which is this tensor itself, 2 tensors, and here I'm building the computational graph. So the first node is the multiply node, multiply underscore node equals D times F. So D times F is this, D times F, and I'm creating another other node that okay equals multiply node plus 5. So this is what I did. The multiply node, let me just change this to multiply and change this to D and F. So this is D, this is F, this is my multiply node. So multiply the 2, they will come up with an output. The other node, so that will be the multiply node, the output of multiply node plus 5. So here I would just erase this line. Let me take out all of this. Okay, let me not just leave it. So the output of this one here will now be coming into another other node, and 5. So here is my 5 in this node here, and whatever it is will be the output of this other node. Let me just say the output is H. The output of this other node is H. So what happened is D times F come out with an output. Now the output is the multiply node output. So that output again plus 5 at this node will give me the output of the other node. So what I need only is to run the other node. Once I run the other node, Tensor will run all the other nodes that I have. So I don't need to run the multiply node separately. I only need to run the last node, the last computational graph, the last node on the computational graph, which is the other node, and with that all the sessions will be run. So here I've built my computational graph. So I'm opening my TensorFlow session here, say ses equals tf.session, and in my print, I'm saying print ses.run. You can see that it's only the other node that I have here, ses.run ada_node. That's what I'm running. However, you recall that I said my D and F are placeholders. So when I'm running my tensor session, I will put the value of my placeholders in a feed dictionary. So ada_node feed_dict equals, this is the dictionary. You recall that to create a dictionary, you use the curly bracket. So D is the key now, and all of this in this list is the value for D. F is the key here, and all of this in this list is the value of F. So that's the key and value for the dictionary for the placeholders. And after then, I'm closing this session. So just run this alone. So it's only the other node I need to run, which is the last node on my computational graph, and I would have the output. So that is one good thing about Tensor. So you just build your computational graph, and after then you run the last node, the last operation on your node of the computational graph, and every other node will be run to give you the output. So here I'm doing the other node equals multiplier underscore node plus 5 as another the same node here, but what I'm doing in this case is I'm increasing my placeholder data as into from just a single row data into a 3x3 array, into a single array, into a 3x3 array. So in this case I have the D again, which is the key here, and I have the first row for D, the second row, the third row, which is a 3x3 array. Also the F has to be a 3x3 so that it can match the 3x3 here as well. So run this, I'll get an output of a 3x3 array. So this is the output of the 3x3 array of this computational graph which I created here for the D and F placeholder tensors that I created. So it's very important to note that your placeholders, the number of elements must be equal. This one is a 3x3, this one is also a 3x3, else there will be an error if I delete just one here to make this one into unequal. You can see that came out with an error, and the error here is saying the requested array has an inhomogeneous shape after one dimension. So the detected shape was 3, plus inhomogeneous part. So what's saying is that this one is a 3 by 3, while this one is missing something. So I'll just need to put any value there. I'm just testing it, so we can see that we have our output. So the third data type in Tensor is the variables or variable. Variable in your Tensor are values that will change as your composition goes along. So when you're saying a particular tensor is a variable, then you're saying that the value of that identifier which you have created as a variable tensor will change in the course of your computational graph. So I have here a mathematical expression y equals 0.2 plus 0.3 times x. So I'm creating my k here as an identifier, and I'm saying this k is tf.variable. Also, notice one thing about the variable TensorFlow data. The v is capital, unlike the placeholder where the p is small letter and the constant where the c is equally small letter. For the variable tensor data type, the v is a capital letter, so it's tf.variable, and in parentheses, the first position in your parentheses is the initial value that you are giving to your variable. Now your variable must have an initial value. The initial value I'm giving to this variable is in a list, and you have 0.5. It's in a list because for mutable data type, list is one of the mutable data type. So that's why it has to be in a list. It can't be in a tuple because the value of a tuple cannot be changed. So in this case, in a list here, 0.5 comma, and I'm saying it's a tf.float32. So it's a float, and the initial value is 0.5 inside a list. Is very important. Also, when you create a variable, a tensor variable, you need this line. Now, the value that you want to take as the initial value for your tensor will not automatically be stored in that identifier, but to actually store this 0.5 as the initial value of this tensor k, variable tensor k, you need to run this line: init equals tf.global_variables_initializer parentheses. This is a constant that you have to run each time you create a variable in Tensor. So init equals tf.global_variables_initializers parentheses. So this line will be the line, and it will come before you run your session. It will come before you run your session. So it's the line that will actually store this initial value of 0.5 into this variable k. So that's what this line is doing. So after then, I'm starting my session here. Ses equals tf.session, and I'm actually running this init. Now you need to create this line and run it in your tensor session. So it's actually the running of this line in your tensor session that would store this 0.5 into this variable k, unlike the constant and the placeholders that you don't need to put this line before you can actually run your sessions. For variables, you must put this line, then start your session, then run this init in your tensor session to actually initialize your variable with the initial value. So ses.run init is where this 0.5 will now be stored in this identifier k, and here I'm now saying ses.run k in the print function. So with this I can get 0.5, and I'm closing my session after that, so I can get 0.5 here. If I don't do this, let me comment this and comment this line and just say ses.run k. You will see that it will come out with an error. You can see there's an error saying that on initialize value variable 1. So you need to initialize it. So to initialize it is what the init is doing, and you need to run that initialization before you can actually run that identifier as it is in the tensor session to get your output. So that's how you do that for the variable. So those are the three data types in Tensor. Now I'm trying to create a linear model. We will recall the equation of a line in mathematics: y equals mx plus c. M is the slope, y, c is the intercept, and x are the values that we already know on the x-axis. So what we're actually after is to know the value of y against the value of x, which we know. So I'm setting up my M because for the equation of a line, the slope of the line and the intercept will change, would vary. However, the x will not vary. So to get a perfect straight line, you need to begin to vary your slope and the intercept to get that. So based on that, I will start up my slope and my intercept as variable in Tensor because I know their value will change. So I'm saying here that m equals tf dot variable, and the initial value I want to put there is 0.8, and it's a float, tf dot float 32. Also my intercept, tf dot variable, the first value there is minus 0.2 comma tf dot float 32. So my intercept and my slope, the values will change, so I'm setting them up as a variable. However, the x, I already know the value of the x. So based on that, my x is a placeholder, which I'm going to put the value when I'm running my session. So x equals tf dot placeholder in bracket tf dot float for the x. Now, because I have two variables, so I have a variable in my data type in Tensor, I need to first of all run the init, that's tf.global underscore variables underscore initializers. I need to put this line, then start my session, run my initializer like I've done here. So after then, this is my computational graph. In this case, y equals m times x plus c. So this is just what I've done here, m times x plus c. So saying m x, so here this is my multiplication, so here is my addition, and my c is coming from here, and here is my output y. So this is my computational graph which I've built, and that's what I'm doing here. So y equals ms plus c. So after building the computational graph, then I'm going to run y. In this case, I'm just going to run y. So p print in test.run, I'm going to run y alone because y is my final operation on my computational graph. So once I run y, every other node would run accordingly. So, and when I'm running y, I need to put the placeholder of x, which I specified as a dictionary. So here's my dictionary. You don't need to always put the feed underscore dict like I did the other time. Just put the dictionary after the comma. So comma, y comma, this is the dictionary, square bracket, x is the key, while all of this list is the value for the dictionary. And I'm closing the session here because I'm using the second method for starting up my Tensor session. So I'll just run this. Now you can see for the first value of x, this is the output of y. For the second value of x, this is the output of y. For the third value, this is the output. For the fourth value, this is the output, and on and on and on till you have this for the value of 9 in x. Now, you can convert from one data type in Tensor to another. What I'm saying is, if you have integer and you want to convert from tf.int to a tf.float, because if you notice, all the data types for the Tensor that we'll be handling, they must be uniform. tf.float, tf.float. Once I have a tf.int here and these ones are floats, before I can work on them, I need to convert them into the same data type, either to convert the two other floats into integers or convert the integer into a float. So that's what I'm doing here, and you use the cast function, the tf dot. So we have here, we have a as a tensor we have created as tf dot constant. The value of that constant is 3.0, and it's a float 32. That is the default for constants. So here we have c, another identifier, tf dot constant, and we have 5. 5 in this case is an integer, So that's why it is tf.int 32 here. So I'm starting my session here with tf.session as says, and I'm saying print. The answer is just a string that we printed alongside the output. Says.run tf.subtract. I want to subtract a from c. tf.subtract a, comma tf.cast c, comma tf.float 32. So let me just explain this part. Now, because c and a are not of the same data type, one is a float and one is an integer, so Tensor will not run in that wise. So I need to put both of them in the same data type. So is that you convert the a into an integer, or you convert the c into a float. So in this case, I've converted the c into a float. So I'm saying says.run tf.subtract a, comma tf.cast is what I'm using to convert from one data type to the other in Tensor. tf.cast. So I want to convert c into what? A float 32. So that is what that is doing. So this is how you can convert from one data type to another if what you're having is not in the same data type. So this is the output, which is minus 2.0. That's for the output that I convert. Okay, so here I'm creating two tensors a and t as placeholders. And I'm using the matrix multiplication here. I'm saying multiply underscore node tf.mathmul. This is matrix multiplication for a, comma t. So which means the two placeholders a and t here are matrix which I want to multiply using the mathmul function in TensorFlow. And I'm creating another adder node here where the multiplier node is being added to 20. So when I'm starting the session here, says equals tf.session, print says.run. I will only run the last node on my computational graph, which is the adder node. That's the adder node, comma. Then this is the dictionary for my placeholders a and t. So for a here is the key. This is the value. You can see it's a 3 by 3. First row, second row, and the third row. Also here, it's a 3 by 3 for t. Because for you to multiply any array together, even if it's matrices, the number of row of the first must equal to the number of column of the other. In this case, I have 3, 3 for a and also 3, 3 for t. So the number of row of a is 3 and the number of column of t is 3. It can be executed in that form. So says.close when I'm done with my session. So here is the output. So also if I want to do my t, I can turn my t into just one colon. So and the number of row of the first, which is 3 row, multiplied by 3 colon in this case. So that would be for 4. Sorry, that'll be 4. This for 8. So they will represent 1 colon each in that manner. And also for 10 in that manner. So 4 is a colon on its own, 8 is a colon, and 10 is a colon. So that is 3 colon, and here is 3 row, 3 colon, and this is just a 3 colon vector. So you see here is the output. If I don't make this into a 3 colon and I just say 8, 4, 8, 10, it's going to come out an error because that will be a row and it will not work in that manner. So let me run this. You can see that this is an error because in this case the 4, 8, 10 is a row. Just like we have here, this is the first row, this is the second row, this is the third row. So here, and I'm saying T has a row, and you cannot multiply 3 row and 3 column matrix here with a single row. Just what I'm saying is this: for you to multiply any matrix, this is the row 3 by 3, So this is the row, this is the colon. So to multiply a matrix, the number of row of one matrix multiplied to the number of colon of the other. So let me say this is my matrix A and this is my matrix B. So the number of row of this one multiplied to the number of colon of the other one. So if the number of row of this one is 3, the number of colon of this one has to be 3 to multiply. So to do that here, to make sure that Tensor recognizes this as individual colon in T, so I need to put them in their own separate list like this. So that's how Tensor recognizes them. Okay, 4 is on the colon, 8 is on the colon, 10 is on the colon. So this is a 1/3 matrix. So in that case, the matrix A is 3/3, while the matrix T is a 1/3. So with that, the number of row of A equals to the number of colon of T, and based on that you can actually multiply them, and that's why you didn't get an error here. So that's very important. Also here again, another example, I have two lists here, A and B. They are list. So I created two placeholders here of Y and K, and I'm using the loss function in Tensor. That's the tf.reduce underscore sum. So just what I'm doing here is I'm doing the SSE, that is the sum of squared error. So sum of squared error, that's SSE. SSE is the sum of squared errors. So this is summation, sum of squared error. So n to infinity or to I to whatever it is. So that will be xi minus oi all squared. So this is the sum of squared error. That's what I'm doing there. So, and in Tensor it is tf.reduce underscore sum, in bracket there are tf.square y minus k. So y minus k. So in this case, this is my y, this is my k. So this is y I minus k I all squared. That's the tf. This is SSE, not SSS. SSE, sum of squared error. So that's tf squared. So I'm squaring the difference here so that I can get the magnitude, and this is the tf.reduce sum so that I can sum this error together. So, and I'm using the identifier loss here, and the mean squared error. The mean squared error is just to divide the sum of squared error by the length of the error. So the loss divided by length of A, because A and B have the same length. Without that, they cannot work. They have to be of the same length. So just pick any length in A or B. So loss divided by length A. So this is my second node. This is my first node. So says.run, I'm starting my session here. Print the mean squared error. The MSC is, I'm using this to format colon.2f. That is the float, because what we're going to get out is a float. So into the 2 decimal place, and I'm using the format function here alongside the loss. So format in brackets says.run the loss, comma, the placeholder for y is A, and so the value of placeholder for y is A. So the dictionary is y is the key, A is the value, comma, for k its value is B, the value of the placeholder k is B, so comma k, and the value of that is B. So that's for the loss, for the MSC, and for the SSE. Even this I need to change it to the MSC. This is MSC, and this is the SSE. This is the SSE. So the loss is the SSE, while the mean underscore error is the MSC. So for the MSC, and the MSC is Also, I'm using the same format, two decimal place dot format says dot run mean underscore error comma the dictionary for the two placeholders y and k, and I'm closing my session also. So we see the SSE is this and the MSE is this. So that is just how you can do your mean squared error or your sum of squared error easily with TensorFlow. So here again I have another instance here. The question is y equals 2x squared plus 5x minus 2, and the value of x are 2, 5, 8, 9, 3. So that tells me that x is a placeholder, my y is the output as the final node. So 2x squared plus 5x minus 2. So a is a constant, is 2 because I know this is 2. Also b is a constant and is 5 because if you look at this is a, b and c. So but c and a are the same value, so I don't need to create any other constant. I'll use a twice in that case. So my x is a placeholder. So this is my y. I'm building my computational graph here. So my y equals tf dot multiply a comma tf dot square x, because this is 2x squared. So tf dot multiply in bracket a comma tf dot x squared. So that's for this plus this is this first 2x squared. So tf dot multiply b comma x, that's 5 times x. So this is the second instance, minus 2, and I've said 2 is a, so minus a. So this is 2 times x squared, and this is 5 times x, and this is the 2 minus a. So I'm starting my session here, and I'm saying print the value of y is this string we printed alongside it. Says.run y is my node that I want to find out the value that will be stored in it, and this is the placeholder for x. That is the dictionary here. X is the key while the list here is the value. So to run this, so the value of y is 16 for 2 of x, 73 for 5 of x, 166 for 8 of x, 205 for 9 of x, and 31 for 3 of x. So with that, we have come to the end of this introductory session to TensorFlow. Thank you very much.